Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right. So thanks everybody for coming. This is a talk from Ayse. Benner? Yeah. And the speaker is going to be Gu Chalikla. Hopefully I got that right.
Yeah.
They're from Ryerson University, and they're going to be giving a talk on confirmation bias and how it affects software engineering. Let me just tell you a little bit about Gu. So she holds a PhD and Master of Science degrees in computer science and a BS in mechanical engineering from
Boğaziçi University.
Boğaziçi University, yes.
She's also
awesome. There's a lot of Turkish people around, which is awesome. She used to be a research and development engineer at Alarco Carrier, and she later was a researcher in the software research lab at the computer engineering department of Boğaziçi University.
Oh my God.
I'll get it right someday. She's currently a postdoc fellow at the Data Science Laboratory at Ryerson University, and she studies empirical software engineering, software management, and cognitive aspects in software engineering, software defect prediction, mining data repositories, and machine learning. So with that, I give you Gu.
Thank you. Thank you, Andy. Hello. First of all, we'd like to thank you for hosting us, and it's a great pleasure to be with you all, guys. So today's talk is going to be about, as Andrew mentioned, confirmation bias as a human aspect in software engineering. But first of all, I'd like to talk about a little bit who we are, where we came from, and how our research originated, and what is our present research, what is our vision in research. So let me give you a brief information about our data science lab. Our lab mainly builds intelligent models to solve problems in software engineering domain, in environmental issues, and in biology. And while doing that, we use some theories from disciplines such as machine learning, artificial intelligence, statistics, psychology, cognitive psychology, and so on. And here is our current staff, and it consists of 3 faculty members from 3 different departments, which are industrial engineering, computer science, and information systems, and a postdoctoral research fellow, that's me, and 3 PhD students, 4 MS students, and we are planning to expand our staff by including 8, 6, or more graduate students. So I guess some of you might know our alumni, PhD alumni. I think these people are familiar to Microsoft Research. Ayse was an intern at Microsoft Cambridge 2 years ago. I think it was in 2010. And last summer, Ekrem was an intern at Microsoft Redmond here. And Burak is from University of Oulu in Finland. He's a researcher there, and he's been doing collaborative research with you about mostly in test-driven development. And over the 12 years, in it our work originates back to 12 years before, and it was originated in Istanbul, Turkey, by Professor Ayse Benner. And our goal is to collaborate with industry as much as we can, because it's very important for us to solve real-life problems. And so we have been collaborating with industry for a very long time in terms of data sharing and sometimes funding, and sometimes in terms of joint publications. And these are our current collaborations and projects. We have been collaborating with IBM in Canada, IBM Toronto Software Laboratories, and mostly with the development team of DB2 for almost 2 or 3 years. And we are also collaborating with Sikkis and Mount Sinai Hospital. So what are our research areas? Well, we have faculty members, and they have their specific research areas other than Professor Benner. Dr. Özgür Türetken is specialized in organization and presentation of information. And Dr. Ali Miri is specialized in privacy preserving, data mining, and cloud. And Professor Benner tries to solve problems in software engineering domain, mostly, and in other domains, and especially in problems in industry, by building intelligent oracles. So, regarding the research of Professor Benner, as I said before, it goes back to about 12 years, and when Software Lab was founded, it started to do research at the intersection of AI and software engineering. So we started to solve problems in software engineering domain using some disciplines, methods, and techniques from artificial intelligence. And our goal was to enhance the performance of defect prediction models. So why do we use defect prediction models? In our labs, we usually use it for the effective allocation of resources before the testing, for the testing phase, so that we can guide the testers, testing project managers, which parts of the software needs to be tested first, or priority, to which parts of software priority should be given, so that we can catch more bugs in less time and losing less money. So first of all, we tried the conventional already existing algorithms and try to find out what is the outcome. And of course, at the same time, there were other researchers who were working in similar subjects with us, and they obtained some very significant results in this field in terms of their performance of their predictors. So first of all, we tried the conventional algorithms. Then we wanted to find out whether it is the problem is in data science, so that is it possible that by increasing the data size, we can increase the performance of our predictors? And we found that by doing methods such as undersampling, even with small data, we can obtain the same results that we obtain with more data. So this means that the problem is probably, it's very highly likely that the problem is not in data size. And it's a good thing because it's not easy to obtain data in software engineering field, and most of it is noisy. So we sometimes, having detected the noisy data, we have to get rid of that part. And what is left with us is something very small. So it's a good sign for us. And also, there is the data content. First of all, we also tried new algorithms, new methods, and we obtained some improvement in the performance. And later, parallel with other researchers, and some of you are here in this room, we tried the file dependency graphs, static code metrics, churn metrics, and also design metrics, which have been extracted from the requirements documents. And these were mainly related to the product itself, software code, and the software processes. But also, there is another thing. Our vision is human aspects need to be integrated into prediction models in order to increase the performance of the predictors, because software is being designed, developed, and tested by people. And so in the literature, there are also some techniques, methods which have been proposed and which gave significant results, like organizational metrics by Nagapan, or social interactions by Bird, Manley, and developer experience by Verifies, and so on. And so we thought that we should go deeper in people. That is what our current research is about, and we're interested mainly in the thought processes of people. And also, another vision of us is, as well as concentrating on the human himself, we also think that tool support is very important. So, because we just want to solve the problems in real life. And so, we developed a tool in our laboratory, and our laboratory's name was previously SoftLab in Istanbul. And it parses the code, and it extracts some metrics and predicts the defective parts of the software by employing some conventional and also new methods in AI and machine learning. And it is an open source code. And based on this previous tool, Prest, we also we have been currently developing another software, which is much more extensive, large scale, and it is a web-based software, and it consists of certain modules. And modules include metric extraction, prediction of the defective parts of the software, effort cost estimation, and reliability release management, reliability prediction of the software. And also there is the people module, so that which can be used also by the HR people for the recruitment of the personnel, performance evaluation of the personnel, and so on. So we said that we have now currently focused on two things: development of a support tool, which helps the practitioners, and also human aspects in defect prediction models. And we want to model human aspects, and we model human aspects in two ways: people as part of a team and people as individuals. So as people, as part of a team, what we look for is a researcher in our lab. He's going to graduate from his PhD. He's going to graduate from his PhD soon. Is mining issue management systems, and is trying to find out who should fix which bug, so that the tasks can be allocated based on the guidance which is given by his models. Now, I'm going to talk about confirmation bias, which is the main subject of this talk. Well, why human aspects in software engineering? Our goal is to enhance decision-making under uncertainty, to guide managers to solve some critical problems in any phase of the software development lifecycle. And these questions can be various. They come up during the daily software engineering activities. And this can be something like, which parts of software should be prioritized for testing? Who should develop the most critical parts of software? Who should fix the bugs in the most problematic parts of software? Who should or should not maintain the same source files, the same source files, or who should we hire as a developer? Or who should fit the profile of a tester, analyst, or designer most? So these are some of the questions, and the list of questions can be extended more. And we want to find out the answers. We want to guide the managers and the professionals in answering such questions. So people's thought processes have a significant impact. I mean, how we solve problems, the way we think, the way we reason, has impact in software itself, in the qualities of the software, because software is designed, tested, developed, and managed by people. And while solving problems in daily life, rather than mathematics or logics, we use some heuristics, shortcuts, because time is limited. And these heuristics are not 100% correct. They're, if you're lucky, 90 or 95% correct, maybe. And when they fail to produce a correct judgment, this may result in a cognitive bias. So cognitive bias is a deviation of the human mind from mathematics and logics. And there are some common cognitive bias types, and there are many. And when you look at Wikipedia, you can see hundreds of different types of cognitive bias, and some of the cognitive bias might be related with each other. And so there is the confirmation bias, there is anchoring and adjustment, availability, and representativeness. Well, so we firstly focused on confirmation bias. And why confirmation bias? So first of all, to answer this question, what is confirmation bias? Well, given some hypotheses, we have the tendency to seek evidence to verify those hypotheses rather than refuting them. We do not have the tendency to find reasons or evidence which can refute our hypothesis. This is a tendency of human beings in real life, and it has some advantages, but on the other hand, it may also have some disadvantages. So in some way, we should have, as well as a verifying mechanism, in some way, we should have also a refuting mechanism going all together. So why confirmation bias? Well, indeed, it all started when I read the article by Stacy and Macmillan in ACM Communications. It's an old article. It was published in 1994 or 1995, but it was an interesting one. It was about, it was a kind of a brainstorming. It didn't present any empirical results, but it was talking about these biases like representativeness, availability, and confirmation bias, and how might these show up in daily software engineering activities, and how might they affect the quality of the software. So then we found, I came across with the work of Teasley, and their empirical results showed that the testers have some tendency to do positive tests rather than preferring negative tests. So as a result, we wanted to search more about the confirmation bias, and we found that the term confirmation bias was used by Wason in cognitive psychology literature almost 60 years ago. And he has some famous tests, psychological experiments, to show the existence of confirmation bias among people. So, and over the 60 years, and Wason also admits that he's surprised that over the 60 years, variations of these psychological experiments have been designed and conducted on people, as well as the replications of the original ones. So there are some publications still going on in this in the subject in cognitive psychology, and it wasn't expected to be that popular. So we had some empirical evidence showing existence of confirmation bias among software people, and also we had some grounded work which ranged across the whole 60 years, and it was something. And we also have been collaborating with professors from the Department of Psychology, and we came with them. We performed some brainstormings, and during our collaborations, they consulted us, and we came up with some methodologies to quantify confirmation bias by taking their consulting them and performing brainstormings, meetings, and so on. So, due to confirmation bias, developers tend to perform unit tests. For instance, if we take developers that make their program work rather than to break their code. We don't say that their ultimate goal should be to break their code. Of course, we need some scenarios for verification purposes, but we mustn't neglect the scenario test scenarios which have the probability to fail our code, so that defects are not overlooked for the testing phase. So we say that during all levels of software testing, we must employ a strategy which includes adequate attempts to fail the code to reduce software defect density. So we wanted to make some empirical research. We wanted to find some answers to questions such as how does confirmation bias, excuse me, yeah, sorry. Yeah.
How do you decide whether a unit test is part of confirmation bias or refutation bias? Because on slides before this, you've done like a difference between refuting and confirming.
Well, unit testing, the goal is to make sure whether that program whether that module, that part of the software works correctly before we can integrate all of them together. So, but when it is, especially when it is our own code, without knowingly, unconsciously, we just want to make it work. So, and there are infinite number of scenarios indeed, and we cannot do exhaustive testing. But most of the time, we are stuck with the on the overall space of possible test scenarios. We are most of the time stuck with the ones which make our program work, and we most of the time do it unconsciously. So, So we wanted to find out what is the effect of confirmation bias on software defect density, and how can we use this information? Are there any ways, perhaps, to circumvent confirmation bias? And this is the question whose answer we are still seeking for. It's very important. But first of all, we had to quantify, in some terms, confirmation bias, because we were working with methodologies like machine learning algorithms, AI methods. I mean, we are using robust Bayes networks nowadays rather than the sophisticated ones, just because there's too much noise in our data. But so at the end, we needed some numbers. And so this was our first challenge in our research. And the question was, how can we identify the measures of confirmation bias in relation to software development process? This was the prerequisite research question that we had to answer before answering the other questions in our minds. So given this challenge, as a part of our brainstormings, collaborations with the psychologists, we came up with a methodology that is which is an iterative process. And so we initially came up with a confirmation bias test. We prepared a confirmation bias test, and it was almost like a compilation of the experiments in psychology, which aimed to show the existence of confirmation bias among people, and as well as the formation of confirmation bias metric set. So we wanted to form, from the outcomes of these confirmation bias tests, which are administered to the software engineers, some metrics. And our test, which we administered, first of all, we administered this test initially to our pilot group, and afterwards we went on to the field and conducted it to various software professionals in various industries from different domains. And it consists of two parts. The first part was interactive test, and it was based on Wason's rule discovery task, which I'm going to talk about soon, and Wason's written test, and it was based on Wason's selection task, and I'm also going to talk about it. The written test was a conventional pen and paper test, and interactive test was one-to-one. So there was a tester and there was a subject, and subject was given some feedback by the tester throughout the whole test protocol. And so we were also doing some sound recording in order to find out the way that he thinks, and at the same time the subject was writing down what he thinks, how he solves the problem, so that we just wanted to find out the patterns of problem solving that he or she follows to find out a solution during the test. And when we come to the written test consists of the questions of abstract and thematic questions, and I'll talk about them more. And as I think it's going to be much clearer when I talk about Wason's selection task. So when we answer abstract questions, logical reasoning is required. Without logical reasoning, it's almost impossible to answer them correctly. But sometimes, in real life also, without logical reasoning, and this is what we do most of the time, we use our daily life experience and some mechanisms like memory queuing to answer questions. So the theme of the question, if it is something close to real life settings, or if it is something close to that we are familiar with, makes it much easier to answer it, to understand, because we can understand it much easier. So we do not need some type of an abstraction to solve it. So there is also, we prepared thematic questions, and also we wanted to find out what if the theme of the questions are from the software development and testing domain. So here is Wason's rule discovery task, and I took this from his original paper, which was published in 1960, I guess. So we also conducted a similar experiment to software developers from various companies. And so subject is initially given 3 numbers. Which conform to a simple rule. It's a very simple rule. And the goal is to find this rule. And this rule is only known by the tester, I mean, who administers the test to the subject. And so the protocol is something like that. You write down three numbers, having seen these numbers, and you write down reasons for choice, why you chose them, what is the specific thing about these three numbers. And then the tester gives feedback just by looking at three numbers, whether those three numbers conform to the rule that he has in his mind, the rule that needs to be discovered by the subject. And he just says it conforms to the rule, the three numbers that you gave conform to the rule, or it does not. And this may go on like this. The subject may give more numbers together with reasons for choice, and they write down their reasons for choice. And at the same time, they may think loud, so we are recording it. And and the subject is given frequently feedback for each instance of three numbers that he gives. And at the end, when he is sure about what the rule is, he announces it, and if the rule is correct, then we are done. So the test is completed. But if it is incorrect, the same protocol may go on. I mean, the subject can give three numbers and reasons for choice and expecting feedback, and thus receiving feedback from the tester whether those three numbers conform to the rule. And it may go on however long the subject wants. And of course, during the protocol, it is also possible to terminate, and the subject may give up the test. He can say, I give up. So, is there a volunteer? We can try it. Do we have? Thank you. Is there anyone who wants to try it? Okay. So initially we have three numbers. Would you like to give three numbers?
I will try to discover the rule based on these numbers. Right?
Yeah, this is a starting point, and probably based on these three numbers, you have some ideas about what.
I will estimate a rule now.
Yeah, you will give some examples and
I
what.
can say like multiply by 2 and start from
No, first of all, you need to give an example. I mean, three numbers.
So, okay, following these numbers.
No, it doesn't have to follow. It doesn't have to be related. Any three numbers that comes to your mind, which is possibly something related with the hypothesis that you have in your mind.
For example, like 8, 10, 12.
Yeah. So why did you choose these three numbers?
I just follow.
Added by 2. So you just followed.
Yeah, starting from 6.
Incremented by 2. So it doesn't have to be something in the number line that you do not have to think about the continuity. You can think about the whole space of three numbers.
I see, okay.
So, okay. But this is the something like
Any number, yeah.
continuation of any number divided by 2. Well, I just look at this and say that it conforms to the rule that I have in mind. And would you like to try any triples? Any other three numbers?
Okay, now I start from.
Mm-hmm. Okay, cool. Cool. And why? Why did?
If it's only even numbers, then these should not be.
Cool. Yeah.
It could be
So I look at these three numbers, and I say that they conform to the rule. Yeah. And what else?
5, 10, 15. Oh, that's the off by 2 rule.
Yeah. So you're testing increments by 2.
Right.
I look at these examples, this example, and I say that it conforms to the rule.
5, 6, 9. Negative 9.
5, 6, 9.
Basically just testing if it's always equidistant between the
Constant increment, whether it increases with constant increments. Well, I look at these three numbers, and I say that it conforms to the rule. Pi and?
100, 100, -10, and pi.
100, -10, and pi. Now you're doing something like almost boundary testing, yeah. Ooh. You can, well, in order to make it much easier, you can be limited to integers. But let's try this. Because, okay, I look at these numbers and I say that they do not conform to the rule. And why did you choose it? Whether 3 random numbers. Mm-hmm. Cool. Yeah, it's a good choice. Check whether well, it doesn't conform to the rule. So I think something is being shaped up in your minds. Would you like to try more? Is there something on your minds? You know it. Yeah, I mean, the subject, sorry? 111. Why? Mm-hmm. Yeah. To check monotonically increasing pattern. Well, it does not conform to the rule. Yeah. Well, let's say that, okay, let's include all integers. And so why did you try this? Test for positive integers. Well, this conforms to the rule. 10,000, 20,000, 10 million. Why?
There is a limit.
This conforms to the rule. And it's a simple rule. Yeah, just try integers and no complex numbers. Yeah. If you feel that you're certain that Yeah. Yeah. That's just that simple. Sorry? Yeah, it was a very simple rule, but almost, I mean, a majority of people came up with with results, which, I mean, the problem was, I just want to explain it. Going forward, I'll come up with that one. Oh no, I shouldn't have done it anyway. The problem is, we most of the time, when we see 246, what comes to our mind? I mean, yeah. So, yeah, even numbers comes to our mind. When we see that, we have some hypotheses on our minds. And one of them is even numbers. Or also mostly we come up with the increasing numbers with increments of 2 or constant increments. And sometimes, mostly people get stuck with those hypotheses that they just do not want to, they just give examples which conform to these rules, such as increments, constant increments, or increments of 2, even numbers with increments of, they sometimes say that even numbers, and then they revert it and say that, okay, I'm going to change the reason. Well, it starts with an even number, and it increases with increments of 2. And it is the same thing as ascending number, even numbers. So, well, we stuck in a space which is a subset of the rule, which is monotonically increasing numbers. And it is only possible to find out that, indeed, that our space of possible instances is not limited with the hypothesis on our minds that we initially come up with. Only by giving examples which do not conform to the rule on our minds. But initially, it is something very, of course, first of all, we give examples which conform to our rule to find out whether our hypotheses are working or not. Then afterwards, we may need some examples like this. For example, 5, 6, 9 is a good example. Or 5, 10, 15, because we came up probably with increments of 2, and even numbers with increases with increments of 2. And later, oh, what if it is not even? Probably. So we want to do some kind of a refutation, and we tried 1, 3, 5. And later, some of you said, yeah, well, maybe it's not by increments of 2. With other constant increments it can be. And maybe no increments at all. And whether it's increasing or not increasing, whether it's something random. So only by using such examples we can break the circle. And we can go further and find out that the rule is monotonically increasing numbers. But it's interesting that majority of the people perform the tests so that their examples were, they just got stuck with answers such as even numbers or monotonic numbers increasing with constant increments. So it was an interesting result for us. And so I also have one test, and this is the last one. So, and this is called Wason's selection task. And the goal is to find out, we are given a statement, and the statement is, the subject is given 4 cards, and they are placed on a table, so the subject can only see one side of the card. And on each side, on one side of each card, there is a number, and on the other side, there is a letter. And we have a statement, and it says that if there's a D on one side of the card, then it has a 3 on its other side. And the goal of the subject is to find out which cards he should turn over, check, to find out whether the statement is valid or not. So what would you think? Which cards you should turn over to find out whether this rule is valid or not, true or false? Only regarding these four. Cool. Yeah. Why? Would you like to explain the reason to the audience, or is it something too clear? Mm-hmm. Yeah, if there is a D on the other side of 7, then this means that not every D has a 3 on this other side. Yeah, that's the correct answer. But most of the subjects prefer to check 3 or just D. So indeed, what we do is something like some simple logic, P implies Q. So in order to find out P implies Q, given P is correct, we have to test whether Q is correct or not. And also, which is equivalent to, indeed, not Q implies not P. So given not Q is correct, which is 7 in our case, we have to check whether not P is correct. Because then our statement fails if not Q is false instead of being true. So, for instance, while we are doing black box testing, as I said before, we have some test cases consistent with the program specification, and we may get stuck with those. But we indeed have to efficiently cover the space of possible scenarios, so that we can also cover the negative tests, which are inconsistent with the program specifications, to find out more defects, to find out the defects in our code, so that they cannot be, they do not propagate to the testing phase, for instance, during unit testing. And this is the similarity. We have to use an effective hypothesis testing strategy to find out the appropriate test scenarios, so that we can test our code effectively and also efficiently. And here is another one. And indeed, it resembles the Wason selection task. What is the analogy? I just wanted to give an idea about what is the analogy between Wason's rule selection task and, for example, let's say unit testing or code reviews, maybe. I took this example from Macmillan and Stacy. It was the paper that inspired me at the beginning. They were having some brainstorming about those ideas. So let's think that we have a program, and it avoids the referencing a null pointer by always checking before for nullity before dereferencing it. And someone tells you that there are actually, let's say, it's a simple scenario. There are, let's say, in our code, 4 sections of the code to be tested. And we have limited time. Maybe we cannot test, let's say 4 is something small, but it can be something more than that maybe. The sections might be too extensive. And so we want to determine which parts of the code needs further investigation. So we say that if a pointer is referenced, then it has to be checked for nullity. And we have section A. It checks whether the pointer is null. And the pointer may or may not have been dereferenced there. Or section B does not check whether the pointer is null. The pointer may or may not be dereferenced there. And section B dereferences the pointer. The pointer may or may not have been checked for nullity. And finally, section D, where does section D does not dereference the pointer, and the pointer may or may not have been checked for nullity. So, which sections need further investigation? Any answers? Mm-hmm. Yeah. Could you tell us the reason for it? Mm-hmm. Mm-hmm. Are there any pacts? Also a stick, yeah. And then skates. Yeah. So, first of all, here, if we dereference a pointer, then we must check whether it has been checked for nullity or not. We must check this one. And also, if it hasn't been checked for nullity, the pointer hasn't been checked for nullity, we have to check whether it has been dereferenced or not. Because if it is not checked for nullity and it was dereferenced, then this means that we have some problems there. So, as a result of our methodology, we came up with some. Well, I'm going to skip this as fast as I can. I know it looks too crowded here. We were building predictive models, so we were trying to find out how to fix that. So, as a result, we came up with this matrix with this metric set, and I'm just going to talk about the interpretation of these metrics a little bit, so that it can be a bit clear what they're all about. Well, this is, for example, this is an example. This is from a case study, a field study that we performed for developers of our GSM telecommunications company, and at the same time, we performed administered these experiments, these tests on computer engineering PhD candidates, and these people had minimum 2 years of experience in software development. So we also had people who had no software development. They were just developing software for themselves, like simulators for their research and so on. But we then had a subgroup which also had development experience, and Levent was also among them, I guess, who took this test. And so he had almost 10 years of development experience. He performed very well, as far as I remember. And so here are these are this gives an idea about the hypothesis testing strategy that the subject follows to find out the correct answer in the interactive test, I mean the number guessing game. For example, here, I think this also probably will look like, when we plot this, it's going to look like something gradually increasing the severity of the tests. We have to do it like that. We have some ideas on our minds. We just check whether we just do some mild tests to find out whether they fit or not. We just do not want to refute them immediately, but afterwards we increase the severity and we try examples which refute them. And afterwards we make some like this, extreme cases like 100 minus 10p or 10,000, 2,000, 10 million, something much more extreme than that, something like boundary testing. And then this means that indeed this is the point where we are sure, almost sure about what it is. And then we can try something very mild. And this is an indication that, showing that the subject is almost close to 100% sure about the rule, what the correct rule is. So this is an ideal pattern, close to ideal pattern. And this was the pattern followed by the PhD students in our previous university. And this is the pattern which was followed by the developers in the GSM telecommunications company. So it is something a little bit fluctuating, and it's also this fluctuation reflected the results, like how many trials they had to do. These people had to try more than once to find the correct rule. They made some incorrect announcements and so on. So on the left side we have the written test outcomes, and this is another metric, for example. And this is in psychology right-hand roots classification of verifiers, falsifiers, and matchers. So if you're a falsifier, you want to refute hypothesis. And if you're a verifier, you just want to verify. Being a falsifier does not mean that solely only trying to falsify something. I mean, it means that you just want to you also include something regarding refutation while you're solving your tests. And there are matchers here. In none of the groups there are matchers, but matchers do not do any logical reasoning. They are not acting in a strategic manner. They just do things. They just match patterns. Like if they have something abstract, they match the numbers and the letters. For example, in the card case, for example, they see D. If there's a D on one side of the card, then there is a 3 on the other side. They just pick up D, letter D, and 3, and then they say that these are the correct answers. They do no logical reasoning. And sometimes there are some outsiders, people who do not belong to any of the previous 3 categories. So we came up with some metrics. We interpreted the results of these metrics. We observed the behavior of the developers and also testers and analysts. And then we wanted to find out. We are trying to find out. We were trying hard to quantify confirmation bias, but this was the motivation. I mean, does this affect software quality? If it doesn't have effects that we can observe, then so we have to find out the answer of this question. So how do confirmation biases of developers affect software quality? And for this purpose, we went to the field again and we administered these tests in 2 companies. And there were 4 project groups in the second company, and in the first company there was 1 project group. And the first company was an independent software vendor, and I think it was Turkey's largest independent software vendor, and it provides ERP software. They are specialized in development of ERP software, and they provide business solutions. And the second company is, I think, Europe's 3rd largest GSM company and telecommunications company. So they write code to advertise their campaigns, and also they have, since from the foundation of the company in 1994, they have code for billing, charging, revenue collection, and these are the much more mission-critical software compared to announcing new campaigns. So in the steps of our analysis, we formed developer groups. I mean, what do we mean by developer groups? Developer groups are the people we mined the history logs of version management systems, and we found out which groups of developers touch the same set of files, because there are some patterns. Some groups of developers touch the same files over the lifespan of the software. And also we performed estimation of confirmation bias matrix values of developer groups. So we had individual values for the matrix, but we had to map it to the developer groups, because indeed our evaluation was not based on the individual performance, because anybody can be responsible for a defect who touches that file. I mean, and it began for a specific release. Any person who touches that file before the code freeze date is responsible, because it is very possible that defect might have propagated over the releases and might not have been noticed. So this was the concept while we were forming our developer groups, and we estimated the developer groups confirmation bias metrics, and also we measured the defect rate, which was for each developer group there were a certain number of files that they developed and maintained, and among these number of files, some of them were defective. So what was this ratio? We estimated it, and we performed correlation analysis between the developer groups' confirmation bias metrics and defect rates. Well, I'm not going to go deeper in this. I know there are too much numbers, and it's a little bit. But for example, let's say that in our case, it didn't happen. But for example, we have something like 5297. Well, in engineering problems, if we have a correlation like something 50, we say that, oh, it's not correlated. But so when I came up with these results were a little bit depressing for me, because I always look for a correlation which is greater than 70 and 80, within that range, then I say that they are correlated. Then we came up with the conventional effect sizes offered by Quinn, a psychologist, and he says that the effect sizes are, for social science, just because we're representing the ideas in terms of constructs rather than directly measuring them, like we do in engineering and other natural sciences. So this limit must be lowered. And so, for example, if we have something which is greater than 52 or 53, it is a large effect. It's regarded as a large effect. And so as a result of this, for example, there was we couldn't observe such case in our case, but sometimes people do not give some examples. They just announce whenever they see. For example, there's a very common pattern that I came across to while I conducted these tests to people. And it was very common. They were seeing 2, 4, 6, and they were trying 8, 10, 12, 1, 3, 5, and then they were saying, announcing numbers, announcing rules, series of rules, without trying. We were saying, yeah, well, the rule is incorrect, and they were announcing another rule and another rule in a row without trying anything else. So it is something related to, they had probably a list of possible hypotheses on their minds, and they were trying to find out whether they're correct or not without any intention of testing it. So they didn't want to check the validity. They just wanted me to tell them directly whether they are correct or not. So it is something which is very highly correlated to software defect density, for instance. Similarly, for example, previously, as you can refer, we have verifiers. And verifiers, if we have the tendency to verify, then this also increases the software defect density. Just only trying to verify is not good for code. So, having found out these results, so we just thought, our goal was to integrate cognitive aspects in defect prediction models so that perhaps we can increase our ultimate vision was that, increase the performance of defect prediction. So our question was how the measures of confirmation bias perform in predicting defect-prone parts of the software. So we used a very simple algorithm just because it's robust, because our data has noise. And we also used, to make a comparison, we used some conventional metrics like static code and churn metrics and confirmation bias metrics. So we constructed models by using any combination of all combinations of 3 different metric types. Only static code, only churn, only confirmation bias, static code and churn together. And we know that in the literature there are remarkable results showing that if you combine static code and churn, performance increases. And static code, confirmation bias going all together, all metrics, and we wanted to see what the result is going to be. So we did some preprocessing, and we used these performance metrics for probability detection, probability of detection of the detection of the, and also the false positives, the balance. And we found that, well, if you look, I used minus if that metric set doesn't exist in building the model, plus if that metric exists in building the model. And for example, when you use static code in this ERP model, we have something like 69%. And when you use only confirmation bias, we have something like 74%. And when we use all metrics, I think it's something due to the correlation of the metrics. Static code, churn, and confirmation bias metrics had excessive amount of correlation with them. So it stayed at 74. So when we look through, we obtained comparable results. If we didn't performed much better, in some cases we may have not, but our results were comparable. And there is one thing interesting about it, and it's that confirmation bias is a single aspect, human aspect. It's not something. If you say, well, we are going to model human, we cannot say that a human consists of only confirmation bias. And probably in cognitive psychology literature and in psychology literature, and probably I am not aware of, but there's an extensive amount of knowledge about people's thought processes. And there also work that has been going on about personality types and basic cognitive aspects and other cognitive biases. And perhaps this may be something much close to, if we find out the appropriate ones, cognitive aspects and other types of things which can model people, then we can be much close to modeling people. And this was just a single aspect. Perhaps this, and this space is much larger. And even with a single aspect, we were able to obtain results which are comparable with the ones such as static code metrics and churn metrics. And this means that we should go further to investigate other human aspects. So, also, now we said that confirmation bias has got to do something with defects. So then probably that something should be done to circumvent the negative effects of confirmation bias. What can be done? Because in the literature there are debiasing techniques, and there's the concept of metacognition. And and in this field people say that, and I haven't gone through it yet, but I'm really interested in it, about the concept of metacognition, and this is my desire to go further in it. For different settings, since techniques for debiasing strategies changes, for different settings it is said that they should be designed individually, because when you change the settings, the debiasing techniques does not work effectively. So it requires a combination of psychologists and computer scientists, software engineers to design such experiments and to find out whether we can find techniques to debias, to fix these issues on our minds. And it's something that can be done, and it's also explained in the book by Kahneman. And it's something very easily, which can be easily read even on a bus or metro. It's called Thinking Slow and Fast, and it combines all these issues, all the work that he has done over the years with Amos Tversky. And it was the work where he interpreted the results for the economics field and won the Nobel Prize in 2002. And he talks about System 1 and System 2. And so System 2, one of them is lazy, thinks much slower, and one of them is fast and use much more heuristics. But sometimes we have to use the one which is slower to tell something and to teach something to the one which works faster. And by interacting these two, perhaps we can change the patterns which works much faster in our unconscious level. And it's possible, as it is said by the experts. So that's why I wanted to find out what factors affect confirmation bias. And this needs to be, I think, extended and replicated and to find more answers. So we wanted to find out what factors affect confirmation bias, like characteristics of the software engineer, education, fields of graduate or undergraduate degrees, or the job title. I mean, does it change whether it's a developer, tester, analyst, or also we included the researchers? By researchers, I just mean the PhD candidates who were actively involved in the research projects, doing publications, and also at the same time, these people had, as I mentioned previously, software development experience in the industry, rather, as well as writing their own code, just for research purposes. So I named them under the name, I categorized them under the name researcher. And also development experience. Does it matter how many years we work as a developer? Does it change the confirmation bias level? Does it make it better or worse? Or testing experience. And we had some confounding factors due to the nature of the data that we collected. We had some confounding factors, and they were not the main factors due to the nature, because we didn't have from this, I mean, 50%, almost close to 50% males or females. Some of the subjects were females, and majority was males, like in most of the software development industries. And also, we wanted to find out about the characteristics of company, whether the company is developing software as a vendor or in-house to solve its own problems, or is it selling it to other people. And so we had one company from Canada, and it's a large-scale company. And they developed the database management software. So that's why country was also a confounding factor, and we just wanted to find out whether this confounding factor affects our results, whether it's significant in our case, because if it is significant, then there might be something of an interaction, and we cannot trace it. And we also had the characteristics of the software product and the development methodology. Some of them were using agile, TDD, and incremental methods. And so the development languages ranges from C, C#, Java, JSP, and the level of domain expertise changed from where you had some information about, for example, telecommunication protocols or case-based, rule-based reasoning. Only rule-based reasoning might be enough. And sometimes you have to know about the design of a database to implement that code. So it changes. Sometimes you do not need to know the theory lying behind to implement something. But for example, if you are developing DBMS, then you have to know about how databases are relational, tuple relational systems and such kind of tuple relational calculus and relational database models are required. But on the other hand, when you are doing something like a banking software, maybe you may use rule-based, case-based reasoning, and it might be enough. So, excluding our pilot group, we had 174 subjects, 18 were researchers, 100 developers, and 30 analysts, and 26 testers. And we had 4 large-scale companies, and 3 SMEs. And 1 company was in Canada, remaining were in Turkey. We performed multi-way analysis using the MATLAB statistics toolbox. Indeed, it looks much more like the regression model, but because you can integrate, as well as the continuous factors, the categorical factors. And we want to use as a response variable a single variable rather than a matrix set, because then we realized that the matrix set is too crowded. Yeah, it's okay for predicting models, building predictive models, but when you use a single, want to do something like a linear regression or ANOVA analysis, then it gets much more complicated. So as a result of it, we just wanted to come up with a single metric, derived metric, and it is something which we call the confirmation bias level, and it is the deviation of confirmation bias matrix values from the corresponding ideal matrix values in terms of the Euclidean distance. So we have the matrix set for a person and the ideal values for each matrix, and that's the Euclidean distance, which is mapped to the 0-1 domain. So everybody had a single number so that we could interpret the effect of the factors on the single number. And here are some significant results. One of the significant results is, well, we couldn't find any significant effect of education so far. I mean, the fields of undergraduate or graduate study, whether it changes. And interestingly, we couldn't find a significant effect of experience in software development or testing. However, we found that TDD developers, when we were hoping about it, performed better at confirmation bias tests, because they, most of the time, they write tests before writing their own code. So they also want to find out where might be the place where my program may fail. They already know it before writing it up to some point. And there are also, and there's something we found out, and it was interesting, that researchers perform better than developers. And what we meant by researchers, I'm going to explain it more. I mean, the researchers were PhD students, but they were the PhD students of computer engineering department in Istanbul. But not all of them were from the undergraduate. Their undergraduate was not from Ivy League universities. And they were from different universities all around Istanbul and Turkey. And they were admitted to the PhD degree. And they had some experience in software development. And besides that, we found out that it's a prerequisite to gain some hypothesis testing skills through some courses. Like each PhD candidate had to take courses like automata and formal models, formal models and automata theory, and they had to pass the test regarding those theorem proving and such kind of stuff during their qualification exams, because it was a prerequisite. So, and these people were doing research actively. They had to do it. Even while they were taking courses and during their qualification exams, they had to do it, and they were being funded by the research projects. So they needed to have hypothesis testing skills. And perhaps it was the reason, probably it was the reason, not perhaps, that because they haven't trained in logical reasoning and hypothesis testing skills, they exhibit less confirmatory behavior. So some practical outcomes. Well, there are trainings in companies. Most of the time there are trainings in Java or a new software, a new tool. But these trainings do not include things about improving the personal skills at the meta level rather than a specific domain. To improve the skills of people at the meta level, we just give them trainings in specific domains. So perhaps the organizations must focus on trainings which try to improve the skills of people in terms of much more abstract reasoning. And as mentioned before, perhaps we should go further and look for things which, such as deviations strategies. Maybe they should be developed. And our goal should be to increase metacognitive awareness among individuals. So our future direction is towards a tool, and we have been developing a tool, which I mentioned, Dione, and currently we are developing the human aspects of the tool. So we have to make things less complicated for the managers, such as Dione. So Dione is, as I said, a matrix collection tool, and also it solves problems like predicting the defect-prone parts of software, cost estimation, and such as. And we also try to find out who should work together in a development team, and whose code must be tested by whom, and who should touch the same files, who should work as a tester, and for example, we can perhaps use this during the recruitment of the personnel or performance evaluation of the personnel. And it's a fact that even however smart we are, we have these biases. And even among very intelligent people, these biases are that do exist. And even people who have been trained in logics, who are expertise in logics and logic, like logic professors, statisticians, they have these biases. So among the majority of people, these biases exist. And I think the solution is we cannot only, even if you hire the people who do not have these biases, it wouldn't be enough for you. So we have to train these people and maybe monitor their performance throughout the trainings. And these are our related publications. So what we are looking for? We're looking for as data science laboratory for collaborations, to work in projects, to formulate new research questions, to understand patterns in software development in real-life settings, and to replicate the learnings in public data sets. And we just want to publish jointly. And I'd like to thank you for your patience and for your time. And if you have any questions, you're welcome. Thank you.
So I might not have gotten it right in the end, but it's like you said in the end that so you have confirmation bias and you have all those other things that might influence if you have a confirmation bias or not. And then you're testing if the confirmation bias is basically affecting the software quality.
Mm-hmm.
Why didn't you test the other factors? They might be more, like how do you say, more determinant or like let's say the experience or something like that might be more of a factor than the confirmation bias itself to determine the software quality in the end.
You say that just because confirmation bias is a construct, perhaps it's much easier to model experience and just.
Well, it seems like the confirmation bias is an aggregate of lots of other things together. And I'm wondering if you should test the more basic factors, the more basic human aspects. If they're more basic human aspects, I'm not sure about that one. To see if you can.
Yeah, it's a good question. it's something perhaps it should be done. I mean, perhaps much more basic cognitive skills can be tested. I don't know right now, maybe short-term memory and such kind of stuff, something much more basic. Well, but first of all, we were just passionate about confirmation bias, and we just wanted to find that perhaps it would be possible to find the components at the basic level. Perhaps at the cognitive level, there are basic cognitive aspects, and combinations of these cognitive aspects might lead to confirmation bias. So there might be a way to model these confirmation bias in terms of these cognitive aspects. And well, I didn't try it further, but it's something that I would be interested as a further project, because if I'm going to discover about other biases, and I'm aware of the fact that they are combinations of some other basic cognitive aspects, so we must go one level down, and we must investigate them, and perhaps afterwards may go up.
I guess you're saying even more straightforward, simple things like age, experience, all that stuff. So when we looked at these simpler factors, we didn't find that experience had a significant effect on anything. So if we had found any of these
we couldn't.
On its own, very significant, we would have checked. On the contrary, experience had no impact, for example. So there are also, it's again part of the biases all of us have. As you said, I highly recommend that slow and fast thinking book. And you know, when you read it, your whole perspective to life really changes. And so we all make certain assumptions about many things. And in most cases, these companies, we have seen that they know a few key developers like managers, and they think that, oh, if I give this job to X person, he is the person who would do it. And it turns out that he or she may not be the right person for that given job. But the manager has that impression because he or she thinks that, you know, this person is the most experienced, this and that. So this is unavoidable, and this is life, but the implications of these, again, when we conducted these tests and presented back results to each of these companies, there were some concerns. People said that, oh, what are we going to do right now? If the majority of people have these biases, are we going to fire them? How are we going to, you know, disclose the results? We said no. A majority in the population, all of us are like this. There are very, very few people who have low biases. And what is the likelihood of those people working in your company? It's almost zero. So that's not the idea. The idea is that, you know, create certain activities instead of having the guy doing 5 days of testing. Just spare one day that they can spend doing extra things to improve these skills. So there are ways you can use de-biasing strategies, and why, you know, jet pilots don't fly every day, and it's a similar thing. So just take the person out of their routine, because if you think that this is an important thing, that the important skill people must have in this domain, then, you know, you can do certain things. You can measure the progress. So today you measure the confirmation bias level, 2 years later measure again and see what the progress has been, and come up with trainings to improve the situation and all that. So
we have an engineering excellence. I'm helping. We're working on training our testers, especially in Bayesian probability theory and information theory. What you talked today has shown me something very subtle that I didn't know. It explains why it's hard to explain Bayes. Because the key in Bayes' theorem, the thing that people most often stumble over, is the probability of the other denominator in the theorem. And the denominator in the theorem is a direct function of the bias that you're talking about here. So you've got me stuck. Here I'm trying to give them a tool to reason better, but they can't reason better with the tool because the bias is what's keeping them from understanding the truth. So how am I going to get past that? don't know. Other than I think once they get exposed to the difference in their thinking. Very simple example. We used it in the talk series later. We did we took signal and noise. That book is another book you should have your reading list.
Signal and noise. Yeah, I should note it down.
So in that book he talks about computing the Bayesian posterior of 9/11. What was the likelihood when that first plane struck a building that we were under attack? It was only 38%. Because it was a very, very low probability that planes hit buildings, as attacked. But after the second attack, it was 98%.
Yeah.
So, and everybody
That's
has that
availability
experience.
bias. Yeah.
So when you go through that vivid personal experience, and you show them mathematics, and you can clue in and show them how to compute the probability of the evidence. And there you have to get used to knowing more than one hypothesis. There the most important thing is that they have to understand that they'll be right more often. They understand how wrong they can be. And that's what the confirmation bias does not do. It protects us from being wrong, psychologically from being wrong. We can break past that and say, wait, it's really critical that I understand the odds of being wrong, because that will improve the odds of being right.
That's true.
So it's almost like we flip the configuration bias on its head and intelligently use this to help, even though it was designed by evolution to protect us from being wrong.
Yeah.
I don't know. It's preventable as this. It's a complicated, way more complicated because we're trying to apply it to the engineering workforce. You're talking about suggesting it or we're doing it.
Okay.
It's very, very hard to do until we get past some of these unknown unknowns that are working there.
I'll ask a short question. In the study with the sequences of numbers or the sets of numbers where they have to come up with a reason or a rule, do you find any differences if you only give them 2 minutes to do it versus 10 minutes? Like if they think they're being rushed, will they rely on
We did it.
bias more?
On purpose, we didn't give any time pressure.
Well, indeed, while I experienced some stuff while I was doing pilot tests. I mean, yeah, we didn't because according to the protocol of the classical test, there wasn't no time pressure. You can try however long you want, but for example, our PhD candidates are a little bit competitive people, and so they just wanted to do it in much shorter and shorter times. And the record was 2 minutes by one person. So everybody was asking the minimum time before starting the test or after the test. What is the minimum time to discover a test? Who discovered it in minimum time? So they tried much effective instances, but I do not know whether the effect was a time constraint because it was only one group and we didn't do it over
But
the
my
groups.
experience, I did 3 days in a row, 40 so people, and in the Turkish company, a few sets of people as well. It's although we say that there's no time pressure,
They feel it sometimes.
They want to. They feel like if it takes too long, it's embarrassing, and they want to, perform. Yeah. So our average was between 15-20 minutes or something like that. And although we didn't give the time pressure, we had an internal protocol. If the person couldn't finish in 45 minutes, we politely, helped the person to announce the rule, but then we disregarded that test, and there were only a few cases.
Yeah,
that
45 minutes, 60 minutes, some of them. 2, 3 points.
So we're kind of out of time, but go ahead, Jessica, and then we'll finish.
Do you have any data that correlates confirmation bias and defect severity? The defects that actually get missed.
Severity.
Are they the important ones or the less important ones?
Yeah, good question.
Very good.
In that data set, we didn't have severity information. We just had the defect information. If we had the information, that's a good thing to look at.
It would be
definitely.
a research question.
And actually, in our last paper last week, we were looking at the groups of people and the defect rates, and we manually, because the data set was not too big, we manually looked at the trends of whether the same people or a few key people were grouped together and they were causing defects constantly, and the answer was yes. But we don't know the defect severity information.
thank our speakers again very much.
Thank you.